Hi, I'm Kieren.
And I'm Riku.
And welcome to Artificially Ever After. For today's episode,
Isambard-AI.
So we're here today in Bristol at the UK's largest and most powerful supercomputer, Isambard-AI. And it's also the 11th most powerful supercomputer globally.
And it's not just powerful, it's also the 4th greenest supercomputer in the world.
So today we're going to get an exclusive tour around inside to see what it actually takes to build AI.
It's nice to be here. Kieren and I, part of Artificially Ever After, looking to demystify the world of AI to the general public. And we are PhD researchers, so for us to see the system that we use almost every day is really exciting. Do you mind just giving a brief introduction and what we're going to talk about today?
Sure, shall I go first?
Of course.
So I'm Simon McIntosh-Smith, I'm the director of the Bristol Centre for Supercomputing. So I'm one of the people behind the Isambard-AI supercomputer we're going to take you to see today.
Thank you so much.
And I'm Emma Rose. I'm the Centre Manager for Bristol Centre for Supercomputing. So I look after all the operations side of the centre and access to Isambard.
I mean, it's a brand new facility. I think we joked about it earlier. Even the barbed wire has done amazingly.
We had to build in a lot of physical security because it's such a valuable resource. So the project is over £200 million of investment. So we had to make sure it was kept nice and safe. So yeah, lots of physical security, big high gates, lots of crash barriers so you couldn't crash a truck in through the fence and things like that. So it's nice and physically secure.
Yeah, so it's actually surprisingly quiet from the outside. I think when we parked up, we were thinking that we'd hear like a large sound.
Yeah,
but
it is pretty quiet. The only things that tend to make noise are the cooling systems, and they have fans, and anything that's sort of moving is the thing that makes the noise. So there are some big fans. On days like today, the fans won't need to be trying that hard because it's quite cool. So it won't be making too much noise. We're actually quite near a major road. We're near the ring road in Bristol, and that actually makes much more noise than the supercomputer does.
I think we made this joke earlier about how we can actually be grateful for the British weather when it comes to building a supercomputer. So
yeah, it makes the cooling cheaper and more effective, actually, more efficient. Yeah. We often call these our Jurassic Park gates because they look a bit like there should be some sort of big dinosaur behind here, kept in. There's a couple of sort of grey, nondescript buildings when you first come in, but they actually do something quite interesting. So the bigger building is actually where all of our transformers are. So we have 5 megawatts of power coming into the site. It comes in at high voltage and we actually need to step that down to a medium voltage, which is what the equipment actually uses. So there's a whole load of transformers in one building. And then on this end, there's a water treatment plant. So we use a lot of water in a closed loop to cool the system down. And that water needs to be very, very pure, very, very high quality. So we don't want any impurities or anything in that water that could start to clog up the equipment. So we have some plant that cleans that all up and pumps that around. We've also got some plumbing in there ready to reuse the waste heat from the site. So we capture all our waste heat as hot water, and we're hoping in the future to do a pilot project where we'll reuse some of that waste heat to actually heat the university building that's next door. Should we head on in and actually have a look at the supercomputer? It's interesting because the supercomputers have become so dense these days, so tightly packed together, that all of the equipment that supports them ends up being bigger in size than the actual computer itself.
Yeah.
So we've got more space dedicated to things like cooling or to the power of the transformers and things like that than to the actual computer itself.
Yeah.
In the past, it would have been the other way around. The computers would have been football field sized and all the other stuff would have been around the edge.
Right.
But the computer shrunk and shrunk and shrunk. Okay, should we go on in?
Second Jurassic Park.
Yes, really heavy. Very, very strong.
Kind of came to a surprise to me, but more from a naive position. That's actually very much a workspace. A lot's going on here.
There's always something going on, so we're always sort of we're very much near the beginning of the service. We went into production in August, but there's always a little bit of something else that we're adding or improving. So there's a bit of work going on. To excuse our mess today, but behind us is Isambard-AI. So it's a big metal building, and it's unusual that it's metal. It's actually a modular data center. So usually data centers are bricks and mortar, but this is a modular data center, which means it's effectively made out of components. They're a bit like big shipping containers. And they were never shipping containers. They were actually purpose built to be a data center. but that they come in pieces about that size so that you can transport them around the country and around the world. Our modular data center was actually built for us in the Netherlands, and it was driven here on 6 trucks, 6 big pieces. It arrived November last year, so it was actually over one of the last weeks of November when it was snowing. We were delivering the system while it was snowing, but it comes basically all prefabricated, so everything inside, apart from the computer itself, was all pre-built, all pre-tested in a factory, and then delivered and then reassembled on site in 2 days.
In 2 days?
Basically built our 5 megawatt data center in 2 days because it was prefabricated elsewhere and then just reassembled on site.
Is that a bit like an IKEA flat pack, but super
IKEA flat pack is a good description, or Lego, people often describe it as well. They've got big bits all pre-built and then just click them back together. So yeah, we have a 5 megawatt system. The main space is about 12 by 12 meters, just over 12 by 12 meters. So it's very, very dense. There's lots of pipe work overhead you're seeing as well. That's all to do with the cooling of the system. So it's actually all direct liquid cooled. It's on a closed loop. So it's using water, but it doesn't consume water. It goes round and round, much like your central heating at home. That's how it works, where cool water comes in from some coolers outside, which we'll show you later on, goes in to cool the supercomputer down, and then we get hot water coming back out off the equipment, and that goes back to the radiators where it's cooled back down again. So they're very, very energy efficient. Gives us, we have data centers have a rating, something called a power usage effectiveness, or PUE. If you ever talk about data centers, you'll often hear about a PUE. And it's a number that's usually 1 point something. So for example, its traditional data center might have a PUE of about 1.5. And that means there's a 50% overhead to cool the data center and power the data center on top of whatever power it takes to actually run the computer. So if you like, the computer is the one factor, and then the point something is what the overhead is. So 1.5, 1.4 is actually pretty good for an air-cooled data center. For these direct liquid cooled systems, you can do much, much better than that. We've got a PUE that's typically under 1.1. So in other words, that's a 10% or less overhead. The last few weeks we've been coming here quite a lot, and the PUE has been about 1.06, 1.07, so it's only a 6 or 7% overhead. That's class leading. So you can't really do much better than that, right? The best you can do would be 0%,
right,
1.0, and obviously you can't quite get to that, but 1.06, 1.07 is class leading.
I was also going to say, one of the other advantages, we talked a bit about noise and how quiet the site felt before. One of the other advantages about direct liquid cooled system is the noise, the reduction in noise. Is when we go inside, you'll see we've got some air conditioning units, but effectively that's the only thing that's making any noise on this inside the data center. And obviously there's a big advantage there for engineers who are working in there. It makes the environment a lot more pleasant for them where they are working. And it also means that we can hold a conversation when we go inside.
Great.
Should we go in and have a look?
Let's do it.
Now it'll be a little bit quieter down at that end because we're near the air conditioning at this end. Yeah, so the artwork is based on, it is a brain. We call it the digital brain. And what a lot of people don't notice, on the outside, the brain is actually made up of cubes, and it is a real 3D model, so it's a genuine 3D model. Right. On the inside, we changed it to little cogs to sort of present the sort of mechanics. And because it's named after Isambard-King Brunel, who's a famous British Victorian engineer from the 1800s. We wanted the clockwork was a bit more Victorian. So it's that sort of clockwork, Victorian style, but digital brain. But welcome to Isambard. So once you're inside, you can't really tell. It's a modular data center. It just looks like any data center, really. But you can just about see in the columns and in the floor where the joins are, where the different pieces were brought in.
Right.
And everything that's sort of inside here, apart from the computer, was all pre-built. So it kind of came like that, and then just gets clicked back together once it's arrived. And once the data center was sort of ready, the actual computer could be delivered. We've got 12 compute cabinets. Each one of these is a compute cabinet, and we can open these up, show you what's going on. So this is one of the Isambard-AI compute cabinets. Lots of pipes. It's very, very quiet. So if this was a more traditional supercomputer, it'd all be air cooled. It'd be really noisy because there's lots of fans blowing air.
Yes.
But there are no fans in here at all. Instead, it's all liquid going around. You can hear a very faint hiss. That's actually the pumps that are pumping the water around. The blue pipes are the cool water that's coming from outside. It's not cold, just cool. It's about 28 degrees.
Right.
And then the warm water's coming off the equipment once the water's flowed around it to cool it all down. So the red pipes are a little bit warmer. And the water's coming out at about 42, 44 degrees.
What is each one going into exactly? Is each one of these like a chip or?
Yeah. So each one of these vertical things is a blade. So we could pull one of these out, and if we did, they're quite long. They're about this long, about this high. And on each one of those blades, there are 2 nodes, so 2 servers, if you like.
Okay.
And in each one of those nodes, in each one of those servers, there's 4 GPUs. So there's actually 8 GPUs in total in each one of these vertical blades. They're NVIDIA Grace hoppers, so they're called GH200. There's 8 of those. Each one of those uses about 700 watts. So if you pulled one of those out, you'd see 8 GPUs. There are 55 blades in each cabinet, so 55 in total, and that gives us 440 GPUs in one cabinet. So in here there are 440 GPUs right now, and it uses about a third of a megawatt. So that's 330 kilowatts is right there. All running. It's running right now, but you can't hear it. Because it's all liquid cooled. It's very, very, very dense. It's also about 4 metric tons. It's about 4 tons of equipment there because it's all so dense.
So 440 for each one, 12 cabinets. So in
12
total,
cabinets.
how many chips are we looking at?
It's 5,280 GPUs in this room, and the room is only just over 12 by 12 meters, so it's amazingly compact.
Yeah.
Now, in the past, this would have been, a football field in size. But because it's liquid cooled, we can now pack these in. If this wasn't liquid cooled, if it was air cooled, it would be about 8 times the physical space.
Wow.
So it would be a lot bigger.
We'll have to get our steps in to look at it all.
You would get your exercise walking around it.
Just noticing here actually there's a couple logos. If you could explain how was this project funded? Is it all government money? I see some more commercial names on the left side here.
Yeah.
The funding itself is all government funding, so it comes from the Department of Science, Innovation and Technology, which is a government department. So that explains their logo at the end here.
Yeah.
So BriCS is Bristol Centre for Supercomputing, that's where we work, and obviously the University of Bristol, which has been incredibly supportive in all of this project, and has really worked with us to bring this to life. DSIT use UKRI because UKRI are experts at allocating funding. They use UKRI to actually allocate the funding and to manage the budgets and the finance on their behalf. National Composite Centre is now actually known as just NCC. That's where we physically are at the moment. So we're in their car park. They are a fully owned subsidiary of the University of Bristol. So they are sort of part of the university as well. But we work very closely with them, obviously, because we are physically in their car park. And then the 3 commercial companies at the end, Hewlett-Packard Enterprise are the people that built the system for us. So this is their system using NVIDIA chips, as Simon says. And I might have to pass over to Simon to explain the ARM.
Yes, so each one of our Grace Hopper GPUs, the Grace part's actually the CPU. So there's a CPU GPU pair for every GH200.
Wow.
And the CPU is actually based on ARM, and ARM is the company that makes the CPU design. A really interesting company based in the UK, actually headquartered in Cambridge in the UK. And we've all got ARM technology on us. So actually ARM is the company that's basically inside every mobile gadget you've got. Your phone, the CPU in your phone is based on ARM. CPU in almost anything you've got that's battery powered will be running on ARM. And now they're also in very high-end servers and GPUs. So ARM is the design of the CPU that NVIDIA uses inside the Grace Hopper GPU.
Okay.
And each one of those CPUs has got 72 cores in it. There's like 72 independent brains that can all be operating at the same time.
Wow.
Times 5,280, which is a lot. It's nearly 400,000 ARM cores in this room.
Wow. I was going to ask what actually is a supercomputer, but maybe does that answer the question? Or
Yeah, so for me a supercomputer it's a computer at a scale that can do something that you would not otherwise be able to do. So way beyond a very powerful laptop or a very high-end workstation or something like that. And I think that the power in Isambard-AI is something like 100,000 or 200,000 times more powerful than a high-end laptop. So it's way beyond anything you could do without it.
Wow.
Yeah, so we've shown you a compute cabinet. We can also show you some of the cooling equipment. So this is the pumps associated with cooling. One of these, it's called a cooling distribution unit, or a CDU, and it's providing all of the pumping for the 3 compute cabinets next door. So the compute cabinets use about 1/3 of a megawatt each. So 3 of those, that's a megawatt of power. It's a megawatt of hot water flowing around. And this set of pumps is basically stainless steel pump work, is pumping the cool water in from outside at 28 degrees through the 3 cabinets next door, and then the warm water is coming back at 40, 42, 44 degrees, going back outside to be cooled back down. So this is what pumping all of that water around those cabinets.
It's surprisingly quiet. I mean, if the computers are getting used a lot, does it become louder? Does that become more? Or?
No, that's about as loud as they get.
Oh, wow.
Yeah. They
It's
don't get
like
any louder.
inside an airplane, kind of. You know, we can have a conversation.
Yeah, that sort of faint hum
Yeah.
going on, but they're pumping quite hard. So all the water's in a closed loop going out to the coolers outside.
So for this is like if ChatGPT had a body, you could say this is it.
Yeah, this is behind every AI, either training them or using them. There are things like this. That's actually where AI runs.
Yeah. Oh wow, I've just seen these signatures. There's some important names, I guess, in the building of this.
They are. When we did our official launch, which was on the 17th of July?
17th of July.
17th of July this year, so 2025. We had some important people come along. So we had Peter Kyle, who was the science minister at the time. He's moved on to another role since then. But also had our local MP was here, 2 very senior people from HPE, who's the system vendor, and NVIDIA, who provide the GPUs. Our main boss, Evelyn Welch, who's the Vice Chancellor of the University of Bristol, and also the local regional mayor, all came along for the official switch on. So we had Peter Carr hit a big red button to officially turn the switch, turn the system on. Yeah. Now we've got on the front, we were looking at where all the compute was and all the GPUs, but on the back we can actually see the networking that connects them all together. If you'd like to see that.
Oh yes, please.
Can we show you? Come and have a look. So we can do that just from this end. So it's very different on the back.
Wow.
Lots and lots and lots of cables. Now, there's a network connection for every GPU. So I said there's 440 GPUs in each cabinet.
Right.
So there's 440 connections at least for every GPU, basically to talk to every other GPU in the whole supercomputer. All the cables go up to the top, and there's various sort of switches that connect them all together. And then there's actually cables you can see going out of the top, and that connects this cabinet to all of the other cabinets. It tends to be copper cables for the short distances, and then it's optical interconnect for connecting the longer distances together. There's another interesting Bristol connection to the network. So the network is from HPE, who designed and built the supercomputer. So it's their own design. It's called Slingshot. It's based on Ethernet, but with their own sort of secret sauce on top of that. And a lot of the design for Slingshot was done right here in Bristol. So a lot of the design team, a lot of the architects behind Slingshot were based in Bristol. That's not why we've got it. That's just a coincidence, but it's a nice thing to mention. So we've got a Bristol designed network and UK designed CPU, so the ARM-based CPU. There's a lot of UK technology in Isambard, which we really like. The network speed is 200 gigabits. So, you know, if you've got a very fast home network connection, you might have 100 megabits. So 200 gigabits is 200,000 megabits.
Oh wow.
Yeah. Per GPU. So there's a lot of bandwidth flying around
That's a lot
over
of
our
data,
heads.
isn't it?
That's another thing that makes a supercomputer, is having that very, very high bandwidth, very low latency to connect all of the parts together. Which also goes in these trays above our heads, connects through into the room next door. In the room next door, that's actually where all the storage lives. So all of the data that's being processed lives on. We've got 25 petabytes of storage. It's all solid state, which means it's all flash. Again, the same sorts of storage as you have maybe in your high-end laptop or your phone. and that's all next door. So all of that data's flowing to and from the supercomputer all over the Slingshot network, all in these trays above our heads. And shall we show you, we've got this interesting building management system, which really is showing you a picture of the whole site and what's going on at the level of chillers, temperatures, flow of water, and what's going on. We're currently stood somewhere about here. We've actually got an alarm going on I think that's because they're doing things on the DC-10 next door. But we can see, for example, the little room next door where all the storage is, says it's currently at 36 degrees. In here we can see the temperatures of water flowing in and out. We can see the total power being used at the moment is 1,700 kilowatts, so in other words 1.7 megawatts.
Right.
And the current power usage effectiveness, so that measure of efficiency, is currently 1.07, so it's only a 7% overhead to cool the system and power the system compared to the power the computer's actually using. That's really, really good.
Wow.
We're very pleased with that.
Because normally that sits at about 1.4, did you say, for your average data center?
Traditional, an air-cooled data center, 1.4, 1.5 would be pretty good.
Wow.
So under 1.1 is really class leading. Right now we can see things like the water going to our big hybrid coolers outside is going to at about 35 degrees, coming back at about 27 degrees. So all of this is monitored remotely as well. So if anything goes on, so this alarm in the DC-10, we know at the moment there's some workers in there doing something, so we're expecting that. Somebody will have noticed that remotely as well, and we can take action. A human being can log in and check what's going on. There's also lots of automatic things set up. So if something suddenly stops, so let's say all the pumps suddenly broke for some reason, that will be noticed immediately, and that would trigger automatic reactions to start switching off the supercomputer so it didn't get too hot and damage itself. And no human being would need to be involved in that. That would just happen automatically. So we've got 5 megawatts of capacity for this space. So you make sure when you're designing it that you've got plenty of spare headroom for a day when it was super busy and it was very hot, so the cooler's having to work extra hard. So you make sure there's plenty of headroom. So we've got 5 megawatts of capacity in total. In reality, we'll probably never use more than, even theoretically, more than 4.1, 4.2. And then the actual maximum we've managed to observe is 3.6. So we've got plenty of headroom. You wouldn't want to actually be using about 5 megawatts. That'd be a bit too close to the limit.
Where does that energy come from? Is it just coming from the main grid, or? Oh, nice.
Yeah, it all comes off the main national grid. University pays for us to have all kind of renewable energy or zero carbon energy for Isambard.
Oh, wow.
So it's all a mix of nuclear and wind, depending on how windy it is, things like that.
So no new power plants are needed to be built?
No. A few megawatts it sounds like a lot, but it's not actually that much. We already had the 5 megawatts of capacity here for the site, so we didn't need to do anything extra. No new substations or anything like that to get the power here. We just had to connect up when we were ready.
That makes a lot of sense. I think a lot of people are concerned about every time they use like an AI system, maybe it's ChatGPT, maybe something else, like how much energy am I using, like am I damaging the environment? But I guess what I'm understanding with Isambard is that it's really environmentally friendly and it's not necessarily putting a large strain on the like critical infrastructure in Bristol.
No, we basically designed it to be as energy efficient as it can be. So we picked the most energy efficient hardware that we could. We run off basically zero carbon electricity.
Yeah.
The cooling system is as energy efficient as it can be. And we're even capturing the waste heat, and we're hoping in the future to reuse the waste heat for heating and things like that. That's about as good as it can get. We can't do much better than that.
Wow.
The alarm's gone off now.
Okay, should we take you outside and have a look at the other things that kind of make this possible?
Please do, yeah.
And we're essentially now following the big pipes that come out from the modular data center. So they're all going over our heads. And they come to these big grey boxes, and those are called pump skids. They're basically big pumps that are pumping all the water around. And they come to these things that look like giant radiators, like you have in the front of a car. And that's exactly what they are. They're just giant radiators. So the water's coming out from the equipment off the supercomputer at about 42, 44 degrees. Goes around these big radiators. On the top, there are these big fans. They're basically sucking air in through the radiators and blowing it out the top. And 90% of the time, that is enough to cool the water back down from the 40 plus degrees C back down to about 28 degrees, which is what we need to cool the system back down. And that's it. So that's very, very energy efficient. It's all very sort of passive components. So one of these big radiators, one of these hybrid coolers, can cool down up to 2 megawatts of heat. So one of these is doing a whole row of Isambard, that's 6 compute cabinets, and there's 2 of them. And so it's running the 2 rows separately. And each one, in the worst case, so on a hot day when it's running flat out, only uses 16 kilowatts to do 2 megawatts of cooling. So it's almost nothing. It's really, you can almost run it off an extension lead. They're very, very efficient. And most of that power is in spinning the fans to suck the air through when it's quite hot. So on a day like right now, it won't be working very hard at all. So very, very energy efficient. When it is hot, so when we had those hot periods this summer when it was over 30 degrees C sustained, then the chillers switch from, they're called dry mode, they switch into wet mode, and they actually start to trickle water down the outside of the radiators. And that means we also add some evaporative cooling to the radiators. They're not just radiating, but they're also using some evaporation. So over the course of a whole year, it's estimated we'll use about the same as 1.5 swimming pools of water, which isn't very much at all. It's about the same average use as 21 homes in the UK, and that's it.
In a whole year?
In a whole year, yeah. In the worst case. So actually, while some big data centers around the world are designed differently and they do consume a lot of water, these sorts of systems, they consume almost no water at all. We can actually touch it and see how warm it is if you want to see. So one of these pipes will be warm and one will be cooler. So that's the warmer one. It's only warm. Oh, that's it. It's not hot, and that's cooler. So you can sort of see. So it's not having to work that hard, and that's the secret to the energy efficiency.
That's crazy.
Not having to work that hard.
Amazing.
I think generally sustainability is important to us. I think you mentioned before Bristol's a very green city, but we're particularly interested about ensuring that everything we do is as sustainable as possible. So obviously it's all the infrastructure, and we said earlier about having the pipe work in place to be able to reuse the heat too. So that's and absolutely one of the key things that we'd like to investigate in the near future is completing the loop of the sustainability side of things and making full use of everything that we're producing as well.
Good to see.
Yeah, and you're also realizing just how much plumbing there is in a supercomputer, right? The actual compute part is relatively small. Most of the site is lots of really big plumbing, and it's all that movement of water and the direct liquid cooling. There's a lot of plumbing, lots of fans for cooling down the water and things like that.
More being built as we speak, it sounds.
Still being finished or improved. But this is what it takes. All the stuff that you guys are doing in your own research, and anyone using AI, this is what you need behind to actually enable that.
Speaking of which, would you mind just giving a high-level overview of what projects are being run here? So it's not all, AI is not just ChatGPT and LLMs, is it?
No, there's much more to it than that. So the big system, we've been up and running since just a few months now, back in August early this year. But we're already up to over 1,300 users. So that's grown really fast, even faster than we expected. And over 350 unique projects across a very broad spectrum. Very interestingly, a lot of the projects are health related. So there's a very high fraction of projects which are to do with, say, drug discovery or understanding disease, or maybe automatically looking at images of potential skin cancers to try and diagnose whether it's cancer or not. All those sorts of things. So a very broad range, but all that still will come under sort of health. But apart from that, we've got people developing large language models for financial technology markets. We've got people doing general large language model training. We've got a very interesting group within the government called the AI Security Institute, and they're doing loads of research on AI security. So how can we guarantee that AIs aren't going to go rogue and take over the world, or that you can't easily jailbreak them and get them to tell you things that they shouldn't tell you about the data they were trained on, or how to do things like build biological weapons or things like that. So that's the AI Security Institute, or AC. They're doing some really amazing research, mostly running on Isambard now.
Where do you see Isambard placed in the UK globally? I mean, it's a huge resource for AI development.
Yeah.
What does this mean for the general public?
Yeah, it puts us right up there internationally. So it's ranked the 11th most powerful supercomputer in the whole world, but that includes commercial computers as well as research ones. So in terms of just research, it's much higher up there, and in Europe even higher again. So we can now do things that are competitive with our international peers anywhere in the world. There's a phrase you probably hear more and more called AI sovereignty.
Yes.
And it's this idea that there's more and more sort of geopolitical uncertainty around the whole world, and we don't know what will happen with that over the coming years. And if AI really is so crucial to our economy and to the growth of the UK and to our research, we kind of need to have control over our own destiny in our own hands, so that somebody couldn't switch off the taps and stop us from having access to this sort of vital technology. So that was really this growing awareness of needing sovereign AI capability. That was one of the motivations for the government investing in Isambard-AI, and there'll be other facilities like Isambard around the country in the future, also that the UK has the ability to develop this technology and use this capability within our own boundaries, no matter what happens in the rest of the world.
So there it is. We hope you enjoyed that as much as we did. It was absolutely amazing to see inside such an incredible facility, the UK's most powerful supercomputer, and what it actually takes to train modern day AI systems. And it's one thing reading about these things and understanding what they look like on paper, which both of us have done a lot of research about data centers, but it's another thing going inside one and actually seeing the nuts and bolts, feeling the temperature in there, hearing the sounds. So we're very honoured to do that, and we hope we could convey that today in this episode. But as always, we'd love for you to interact and get involved in the conversation, as this doesn't involve just the people working on it, it affects everyone. Like those kind of applications Simon was discussing, they are there to benefit the people and society more broadly. So please get involved in the conversation, let us know how you feel and what you think about this. But yeah, thank you so much for listening, and we'll catch you next time.